So last time, you not necessarily know what we did last time, but we discussed differentials of maps like diffeomorphisms, embeddings, and so on. And several statements actually were formulated but not proven. Do you know, Patrick, do you know what differential is? Because I will discuss it today, so if you don't know, I can. Yes, so if you have a map, smooth map of one manifold and another manifold. Well, before that, we discussed tangent vectors. And tangent vectors at every point of a manifold form a vector space whose dimension is equal to the dimension of this manifold. If you have a smooth map of one manifold and another manifold, then there is a map between tangent vectors. So if a point P of a manifold M is mapped by in the point Q of manifold N, I mean smooth map of M into N, then necessarily there arises a linear map of the space of tangent vectors at P into the space of tangent vector of Q. This is called the differential. There are notations. I hope you will understand this. But the main notation was, by the way, before that, I didn't feel obliged to denote manifolds by some fixed letters. But today I will have to discuss different things. And I need some amount of notations. So in my lecture today, at least, I will use the capital letters M and N for manifolds. M is natural because it's manifold. N is just next letter of the alphabet. And then I will consider smooth maps, M into N, if P is an M and Q is f of P, which is an N. Then there arises a map which was called dP f T P M into T Q N. This is a linear map, which is called the differential of f at the point P. Now, last time I explained, this was done fully. Well, first of all, always we discussed, but this is very simple, that if this map actually is a diffeomorphism, now this is an isomorphism. And this is very clear. The same is true if M is not precisely the same as N, if M is an open subset in N. So F is an embedding inclusion map of the open subset in N into N. Then again, this is an isomorphism. Then we consider the case when F been embedding, that is a diffeomorphism of the manifold M onto a submanifold of N. Then also I explain this, I will not repeat the arguments. That so M actually is a submanifold of N, and I do not need to use this special letter F, but still. So for every P in M is also a point of N, I explain that TP M becomes just a subspace of TP N. Dimensions of M and N of the manifolds correspond to the dimensions of the spaces of the manifolds, M and N. Now, if there is a tangent vector C to M, then it is also a tangent vector to N. And the fact that this tangent vector to N is contained in TPM is expressed by these words that Xi is tangent to M at P. So to express this, I say that Xi is tangent to M. And now there are two statements which I formulated, but I will give a short proof now. Two statements which actually can detect whether a given vector in Tpn is tangent to M. Statement 1. So proposition 1. Xi in Tpn is tangent to M, same as belongs to Tpn M. If and only if for every function f, f is bad because f have h on n, actually we can consider a function which is given, is defined only some neighborhood of the point P, such that the restriction of the function to M is 0 for h M, you remember, ch, you remember, we can apply tangent vectors to functions, and we get numbers. This is 0. So the statement is that a tangent vector to n is tangent to M. If it don't leave, it vanishes at every function which is 0, whose restriction to M is 0. Do you understand this? Questions about the statement? Because the proof is very simple. Proof will not reveal much. The fact, we have, imagine a manifold, a submanifold, and a point in this submanifold, which is also a point of manifold. And then tangent vector to the manifold, to the big manifold, to the whole manifold. But it may be tangent to the submanifold. And this is precisely the condition which it should satisfy if we want this tangent to M. Let me prove it. If we don't leave, so two statements actually. One is obvious, namely, H restricted to M is the same as H F. Remember, F was my embedding of M into N. This is the same. So I take a point in M, I embed it into, I consider it as a point in N, and I apply H. Then, certainly, you remember there exists the differential. There exists a differential dpf, which in this case is just the embedding. So this differential applied to H by definition is dp of hf, and if this is 0, then this is 0. So this is proven that the vector xi dp, wrong notations, xi here and xi here. Dp xi is defined by this way. So this is 0. Now, the other statement which we need to prove. I suppose now that xi belongs to Tpm. And I want to prove that, no, excuse me, I suppose now that xi is 0 if h m is 0. How to prove now that xi is, so xi is a tangent vector to n. And I want to prove that in this case, so xi is in T, P, n. And from this I want to deduce that xi actually belongs to T, P, m. How to prove this? Suppose that we have an arbitrary function g on M. Given maybe the whole manifold M, or in the neighborhood of the point P, it is not important for us. But what is important, that is that I can, so imagine that this is M, this is P, this is N, and I have some function given, then I can extend it. Function g I can extend to the function g tilde, given in the neighborhood of P in N. After all, you remember that the submanifolds is given in local coordinates in a canonical way, so certainly we can make this new function. And then simply I define a tangent vector on, so now I define a tangent vector to M in the following way. I say that eta of g is equal to xi of g tilde. G tilde is a function which extends g. Here I write this equation. Why? Why it is true that this does not depend on the extension. We could find a different extension. So is it also true equal to g double tilde, where g double tilde is a different extension of g? I say yes, because g double tilde and g tilde are the same on M. So the difference is 0 on M. And by this reason, xi is 0 on this difference. It was my assumption. Or this is equal to this. So this definition, this function f is well defined, doesn't depend on this. And it is immediately obvious that dpf of eta, this is just by definition, is equal to xi. So a vector xi which vanishes on all functions which are 0, has 0 restriction to M, such vector has tangent to M. This is my first statement. Questions? Virgil? Maria? Where's Maria? No. Patrick? Can you understand what's going on? You missed a couple of lectures. You have my notes, so you could look through them on your way to this room. Nothing difficult for you. Now statement 2. So statement 1, in some sense, not very convenient for practical use, because if you have a tangent vector to n, then to conclude that it's actually tangent to M, we need to find its value on all functions which are 0 on M. There are many such functions. it is not very possible to do this. So my second statement doesn't have this drawback. It is actually very useful practically, and maybe in the future we will use it. Now I suppose for my proposition 2. Now I suppose that M, submanifold M in N, locally at its point P is given by F system of equations, so that these functions capital F's, so M and N, this N and this M are dimensions of these two manifolds. This system of functions should be independent in the sense that for local coordinates x1, xn at the point neighborhood of point P and N, the matrix dfi dxj has the maximum possible rank, that is n minus m. You understand, my functions are functions on n, not on the whole manifold n, even locally, at the point P. Still, again, locally at the point P, they depend on local coordinates. There are n of them, Nick, x1, xn. And we can't find partial derivatives of these functions. This matrix is not a correct matrix. It's because there are n minus m i's and n j's. So this is such a rectangular matrix. And this statement means the rank is maximal. That is, there are, so this means that there are coordinates xj1, xj, n minus m. So not all coordinates, but only these coordinates. Say that the determinant of this matrix, which now has determinants, n minus m cross n minus m is not equal to 0. So this is the usual way how we determine a submanifold. It's given locally by a system of equations, independent equations, whose number is equal to the difference of dimensions. People say codimension of the manifold. Now my statement. So this was, I just repeated the construction, but the statement is that the vector xc in Tpn is tangent to M if and only if xc f I is 0, I 1 to n minus m. So this shows that to determine whether xc is tangent to m, we do not need to check the condition from proposition 1 on every function. We just need to check it on these n minus m functions. Understand? Finitely many functions. And actually, still we need to do something to determine whether vector tangent to m. This is certainly the best way of determining it. Just to plug into xc these functions, right left-hand sides of the equations which determine m. If the result is always 0, then the vector is tangent to m. If it is not 0, at least for one of these functions, then it is not tangent to m. That's all. So this is certainly looks much more realistic to check. Now, why so? So we have TPM, we have TPN, and also I define a subspace in TPN which consists of those Xi which are 0 on this n minus m functions. My statement is that this is TPM, right? Let us compare now this space V and TPM. First, if Xi is in TPM, then Xi is 0 on any function which is 0 on M. In particular, it is 0 on every Fi. Fi's are 0 on my submanifold. This is actually my description of the submanifold. So this is 0. So this means that Xi belongs also to V. That is, V is contained in TPM. This is obvious. But why it is equal to TPM? And here we do something which actually you should have some intuition for this. Sometimes we prove such statements in an absolutely formal way. That is, just apply the definition without even thinking what these letters mean. But sometimes we need to use something not contained in these letters. And in this case, as in many other cases, this something is the fact that the manifold is finite dimensional. Actually, there exists a theory of infinite dimensional manifolds. And for infinite dimensional manifolds, it is very much not this clear what I say. So look. You remember that I have this property of the function f. The derivative is not 0. This means actually that if we take any linear combination, non-zero linear combination, if Xi, let me write eta, is a non-zero linear combination, well, with some real coefficients, of dj1, dj n minus m, then eta of f I is not 0 for some I. That is, eta is not in V. It precisely means this. The rows of this matrix are linearly independent. If you apply one of these derivatives to Fi's, you get a row of this matrix. No linear combination of these rows is 0. So this means that no linear combination of the derivatives dji can be 0 on F's. So eta is not in V. What do we have? These derivatives are linearly independent. So there is an n minus m dimensional subspace of TPN I can denote it as W, such that the intersection of V and W is 0. This settles everything. Imagine that in a space of some dimension, in a space of dimension 10, we have a subspace, and say a 6-dimensional subspace which does not intersect, which has only 0 in common with subspace. And my subspace has dimension at most 4. You understand? If we have a subspace of R3, for example, and a 2-dimensional subspace, which doesn't have common vectors with this subspace of R3 except 0, then my subspace has dimension 0 or 1. So from this it follows that the dimension of V is at most, is at least, is at most n minus m. And from my previous statement, it follows that V is TPM. V cannot be any bigger than TPM. By the way, it seems to me that here my inclusion symbol should be reversed. Excuse me, please, and correct it in your notes if you take any. Yes, so my statement has been proven. Two more statements, questions about this. This is important. My second theory is important because sometimes we will have to determine whether a given vector is tangent to a submanifold or not. And my result shows that it is not very hard to do. We just need to find the value of this vector on the left-hand sides of equations. Just finish the sentence, and I will be happy to answer a question. Just should plug into my vector this left-hand sides of equations which determine the submanifold. If they are all 0, then it is tangent to the submanifold. If not, then not. Yes, Patrick?
For your dimension, V should be at most m, not.
Dimension should be not more than that. And if V contains an n minus m dimensional space TPM, I understand what you say. Not n minus m. Oh, Patrick, you help me a lot. M. Yes, certainly m. Certainly m, because there is an n minus m dimensional space which is transverse to this subspace. Thank you, Patrick. Now, two more statements. I don't know, I wanted to say something else, so maybe I will prove only one of them. We see from all this, actually, it was explained last time, that an embedding, if a map of one manifold in another manifold is an embedding, then its differential is 1-to-1. Has no kernel. In algebra, such maps are called monomorphisms. 1-to-1 map. Embedding of TPM and TPN. And this fact is very much local, because when we prove it, we never use the whole manifold. We always speak of a neighborhood of some point. From this, it is clear, and I also said this last time, that this fact, that differential is a monomorphism, is true not only for embeddings, but also for local embeddings, which are called in topology immersions. An immersion of one manifold into another manifold is a smooth map whose restriction to a neighborhood of every given point is an embedding. And this is not a new result for us, but still it is important that if a map, smooth map of one manifold into another manifold is not an embedding but rather an immersion, then still its differential is one-to-one. But there is a much less obvious statement, which the proof is very obvious. I'm not sure that I want to discuss it today. It is written in my notes. But anyhow, it is true that if a smooth map of M into N has this property, namely that its differential at every point of M is one-to-one, then it is an immersion. So actually you can say that a map is an immersion if and only if its differential, it never takes any non-zero tangent vector to M into a zero tangent vector to N. This is actually a criterion. A map is an immersion. Is it true? No, it cannot be true. That actually immersions and embeddings are the same. Certainly not. Immersions allows self-intersections. Even every self-intersecting curve in plane, you can easily imagine such a thing, can be regarded as an immersion of a line into the plane, but not as an embedding. It's not embedding because it's not one-to-one. So the most visible property of embeddings, which does not hold for immersions, is the fact that an embedding is one-to-one. And maybe you could think, if I didn't say 1,000,001 times, that it is not true. Maybe you would think that actually this is precisely what an embedding is. It is a one-to-one immersion. As it often happens, this statement that embedding is the same as a one-to-one immersion is both true and false. It is false because it is false. There are counterexamples. So we compare one-to-one immersions and embeddings. Are they the same? Now I draw this. An immersion of an interval into the plane. My blackboard is the manifold N. The interval is the manifold M. The map is shown on this picture, and it is very clear that the image, I mean that actually we reach here this curve. The image of this map is not a submanifold of the plane, but it is one-to-one immersion. No 2 points of the open intervals are mapped into the same point of the plane. Patrick, you have doubts? You have doubts? No. This is an example. There are certain other examples. But this is an example of a smooth map of a one-dimensional manifold, also known as a line, into a two-dimensional manifold, also known as a plane, which is locally, certainly it is an embedding. Every point of M has a neighborhood for which this is an embedding. So this is an immersion. It's one-to-one because no 2 points of the interval, open interval, have the same image. And it cannot be an embedding simply because its image is not a submanifold of the plane. There is one point, I mean this point. And it is clear that no chart of the plane at this point satisfies the condition which makes this a submanifold. So this is not submanifold. This example shows that my statement is false. But still it is true in the most important case. In the case when the manifold to which we apply our map, M, is compact. So this is statement 1. And statement 2, that if M is compact and N is arbitrary, then any immersion, any one-to-one immersion of M into N is an embedding. Its image is as a manifold. A line with your kind permission is not compact. So this example exists mostly because we apply the map to a non-compact manifold. Both statements are proven in my notes. I want to say something else in the remaining 13 minutes, so I will not prove them. And it will be especially challenging for you to read in my notes the proof of the second statement, because I also read it, and it contains 2 misprints in the most important places. Certainly I will correct them, and I will mail to you a corrected version of my notes. But if you have the notes as they are now, it will be a challenge to you to understand what should be written there. Both statements, actually, this first statement that every map whose differential is 1-to-1 is an immersion is a direct consequence of the inverse function theorem, which we also apply to similar things here. And the second statement has a very direct proof, even not using precisely the definition of compactness. It uses less. It uses the fact that if you have a continuous map, then the image of a compact set is closed. So this is what we actually need. Now I don't want to speak about this. At least don't want to go beyond answering questions which you will ask now. What about questions? No? Virgil? Maria, I don't see her. Then you, Patrick. You see, your classmates do not want to ask questions, so somebody should do it. So do you have questions? I understand that you don't remember some definitions. What about this? Do you understand what I said? Well, yes or no, but I think it is understandable, even if you don't remember precisely the definitions. Because now I want to give another definition. There are vectors, there are vector fields. Have you ever heard the word vector field? Please don't say no, because I won't believe anyhow. So what is the difference between vectors and vector fields? So this blackboard is our manifold. This is a point. This is a tangent vector to the manifold. And this is a vector field. I think this picture says a lot about this. But you know, this is a course in topology. Topology is part of geometry, so this course is supposed to be geometric. But still, my definition of a vector, tangent vector, was not precisely geometric, but more analytical than geometric. You remember, a tangent vector is a function which assigns to every function on M, on the manifold, some number. And also we have some fixed point in the manifold, tangent vector at P in M, and then some condition which is called in elementary calculus the product rule. So if you apply, just for a second, I want a favor from you. Forget all these manifolds. Let us speak about things which everybody knows. Manifolds are not. If we have a function on a manifold, on plane, or whatever, and the vector, then we can find the derivative of this function at this point in the direction of this vector, and this will be a number, right? So every vector is actually has this ability to rework functions into numbers. If you apply just one tangent vector to a function, then we get a number. And then this is my definition of a tangent vector. It is a linear map of functions into numbers, which satisfy this product rule. Now, can we apply a vector field to a function? Forget all these complicated things. Answer what you see immediately. Suppose that, yes, on this blackboard, we have a function, well, two variables, and a vector field. Can we apply not just one vector, but the whole vector field to a function? If yes, then what will we get? Patrick? We have a function and a vector field, so a vector at every point. Just a little bit louder. So we have a function, f on this manifold, and a vector field, so a vector at every point. Is it possible to apply this vector field to this function? Yes, and what will we get? A number? 0. We have a vector at every point. So at every point we can find the derivative of the function which is determined by this vector. This point, this, every point. But vector field consists of vectors given everywhere. So if we apply a vector field to a function, then we get. Yes, thank you, Maria. I almost don't see you. We can get another function. From the algebraic point of view, it is a gift, because it is very inconvenient when something transforms elements of one set. And here, so a vector field has this ability. It reworks functions into functions. And now it is time to give a definition of a vector field. Back to all our theory, manifolds. So we have a manifold M. It's a manifold. A vector field X, this is where I need my notation X, is a map of functions into functions. Yes, which satisfies the conditions which you are going to formulate now. First, this map should be, if you apply it to the sum of two functions, you will get the sum, right? If you apply it to function times a number, you will get the result will be multiplied by a number, right? Such maps are also called linear. So this is a linear map of this space. In this space, we should satisfy one condition. The same as for vectors, but now it looks much more natural. If you apply this to the product of two functions, then we'll get this expression. This equality is called the product rule. And please, please, please do not say to me that you don't know this product rule. If you had at most C- in your calculus class, which I believe you had, then certainly you should know this rule, right? And this is my definition. You know, in algebra, there are algebraics. In algebra, people know this definition very well. If you have not C infinity M, you have some ring, or maybe it's better some algebra or some field. Then a map of this ring or algebra into itself is called a derivation. Derivation. If it is linear, well, algebra is a vector space. If it is linear, plus it should satisfy this product rule. So this is my definition, which can be applied actually to any ring. It is very important in many parts of mathematics. Even difficult for me to list substantial part of them. In algebra in general. In the Lie theory, very important. In algebraic geometry, immensely important. This small thing that actually derivations, you can call them vector fields if you prefer this geometric terminology. Derivations exist, can be considered for basically any ring, certainly, but linear, so linearity, so better to apply this to algebras or some field. Not necessarily real numbers. There are other fields, like complex numbers, but those of you who like algebra know probably a whole lot of examples of vector fields, fields. So this is a vector field on a manifold, a derivation of the ring of functions of these manifolds. Let me again briefly mention in the remaining minute and a half what I'm going to do next. First, functions, if you don't know, have values. Because if a function, we can evaluate it at every point, right? If we have a vector field, X, then you can do the following. You can apply it to some function f, that's okay, and then you take the value of the function at some point. We will get a correspondence, a function which assigns to a function actually a number. And this is certainly a tangent vector. So we have a vector field that as soon as you fix a point, you get a vector. In this sense, vector field is a vector field. A vector field actually consists of vectors at all points of the manifold. Before I speak of other properties, and I don't have time today to speak of them, I want to place here in the remaining 5 seconds an algebraic question. So, a derivation, in particular vector field, is a map of C infinity M into C infinity M. If you have 2 vector fields, then you can take composition, because each is a map of C infinity M and C infinity M. My question, do you think that this composition is also a vector field? No. Right. A composition X, composition Y is not a vector field, but the commutator X composition Y minus Y composition X is a vector field. So for vector fields, there is no operation of composition, but there is an operation of taking taking commutators. This is, we open a small gate, which leads us to a very beautiful theory of Lie algebras, of such things. We will discuss this very briefly here and more in more details if you will attend my lectures in Lie theory next quarter. Thank you very much for your time, and see you next.